أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. Path loss or path attenuation is the reduction in power density of electromagnetic waves as it travels through various space between transmitter and receiver. Path loss is a major component in the analysis and design of link budget for telecommunication system. Pathloss model is essential for estimating the attenuation of radio signal as they propagate through a wireless communication channel. In this unit, we will study various topics, such as we will discuss a drawback of free space path loss model. Then we study uh, path space exponent factor, and then we discuss about path loss exponent web table, and finally we discuss about how path loss exponent values are calculated. While free space path loss models are simple and widely used in microwave communication, wireless communication for initial estimation, they have certain drawbacks and limitations. Some of the drawback of free path space model is lack of environment. For example, this model assumes an idealized scenario of free space propagation without considering the impact of environmental factors. In reality, wireless signals encounters many obstacles due to building, terrain variation, vegetation, and many other objects that can significantly affect the propagation characteristic. Free space path loss model do not account for these effects, leading to inaccurate prediction in real-world scenarios. Similarly, frequency dependent is another important drawback because free space path loss model assume that all frequency experience the same loss rate. With distance, however, we know that different frequency can have varying propagation characteristic due to phenomena such as absorption, scattering, and diffraction. So free space path loss model do not capture these frequency dependent effects, which can result in discrepancies between predicted and actual path loss. Similarly, ignoring multipath fading occurs when signal takes multiple paths and interfere with each other at receiver side. This phenomenon is particularly prevalent in urban environment, causing signal fluctuation and attenuation. Free space path loss model do not account for multiple path fading and due to inaccurate and which lead to the inaccurate prediction of signal strength and quality in areas with significant multiple path propagation exist. Limited accuracy in a non-ideal environment is another important drawbacks because free space path loss model assume an open, unobstructed environment without any interference. In reality, wireless signal encounter various obstacles such as building, trees, and terrain irregularities, which can cause diffraction, reflection, and shadowing. These effects are not considered in the free space model, leading to deviation from predicted and actual path loss in real world environment. Another important drawback is simplified antenna assumption because free space path loss model assume idealized isotropic antenna, which radiate power uniformly in all directions. However, in the real world, antennas have a specific radiation pattern and gains, which can affect the received power and path loss. So, free space path loss model do not account for the characteristic of practicality of the antennas, leading to discrepancies in predicted path and loss values. To overcome all these limitations, more sophisticated path loss models such as empirical model or true ray tracing simulation models are employed. These models take into account environmental factors, frequency-dependent factors, multipath fading, and antenna characteristics, resulting in more accurate prediction of path loss in a specific scenario. The term empirical path loss model is another name for path loss exponent model. And practical systems encompasses various form of obstruction, and each obstruction can result in reflection, scattering, diffraction, absorption, or maybe combination of some of these effects. The path loss exponent, commonly represented by symbol n, is a parameter utilized in path loss model to describe the characteristic of a real-world wireless channel. According to the numerous measurement studies, it is observed that the wireless channel propagation uh, characteristics are reflected by this end, and they are influenced by the factors such as environmental, frequency, and obstacles. The path loss model can be defined as equation Pt over Pr is equal to 4 pi lambda squared d power n. T is the distance, n is a coefficient, and when it convert into decimal form, so we can write 20 log f plus 10 and log d minus 147.56 decimal. This model offers a rough estimation of path loss and can be valuable for designing wireless communication system optimization, antenna positioning, and forecasting the actual signal coverage. Empirical path loss model offer several advantage, and some of these advantage are accounting for environmental factors, most important parameters, and flexibility. It has a great flexibility and adaptability. It is frequency dependent, and this model incorporate path loss exponent, which is validation with the real world measurements. As compared to the free space model, it is much better with respect to obstacles and shadowing. So all these factors make this model is relatively improved version of free space model. In this model, n is estimated by considering many important channel characteristics. Overall, path loss exponent model offer improved accuracy and flexibility compared to simple free space path loss model. Nevertheless, it is crucial to acknowledge that the actual transmission of a wireless communication signal in the real world is influenced by numerous additional elements that are not considered in this model also. So it is open topic for the research, and more sophisticated modeling techniques and measurement may be necessary to achieve a precise prediction of the path losses required for the electromagnetic flow movement from one location to the another location. In wireless communication studies, practically path loss is represented by the path loss exponent, whose value is normally in the range of 2 to 4, where 2 for propagation in free space and 4 is relatively lossy environment. And for case of fully specular reflection from the Earth surface referred as a flatted Earth model. In some environment, the path loss exponent can be reach value in a range of 4 to 6. One of the other hand, a tunnel which practically act as a waveguide, resulting in the path loss exponent less than 2. If you see the table, you will observe that urban area cellular radio, the path value is 2.7 to 3.5, and shadow cellular radio, we use n value from 3 to 5. In building line of sight, which behave just like as a tube, 1.6 to 1.8, and obstruction in building, which is very high obstruction, particularly small areas, 4.4 to 6, and obstruction in the factories is a 2 to 3. In next slide, we will discuss that how these value n are calculated for design of path loss exponent model. A path loss table is created through a combination of measurement and modeling techniques. The process began with measurement campaign where data On-site strength is collected at different dynamics and with different distances from the transmitters. A statistical analysis is then used to identify pattern and trends. The path loss model with empirical relation is then developed, capture the observed relationship between signal strength and distances. Parameters are estimated using fitting techniques, and the model is validated using additional data or references value. The final step is compiling the path loss table, which include environmental specified path loss values. Path loss tables are specific to the environment and condition and should be periodically updated to account for change in the environment or technological advancement.